Since nobody else is doing the job, I will introduce my good friend Bruno Augenstein, who will tell us about interstellar space exploration. Bruno and I worked for a long time on antimatter and antimatter propulsion. He's at Rand Corporation and was the chairman of a very large workshop which really studied how to make and store and use antimatter for propulsion. And he ended up with a conference proceedings that costs $125 to buy now. He's editor of that. And but I think he's going to do something more than just antimatter in his talk. Bruno?
Actually, what I'm going to do is I'm going to take pity on you, because I'm not going to ask you to remember any equations or any numbers. On the other hand, I would like you to think about reading some of the quotations I will put on the screen, starting with the first few read. People were thinking about interstellar travel a long, long time ago. It's an old subject, and one which is generating a lot of interest today. Next few graphs. I want to talk about 5 topics, and you'll notice that technology is only one of these topics. The more I've thought about this topic, the more I've become convinced that really philosophical and cultural issues are really some of the things that are either going to make or break this kind of program. So I plan to spend a little time on some of those aspects also. Next one, graph, please. Now, there's a lot that has to go on in interstellar exploration, and obviously none of us here can predict the future very well, so what I'm going to do is try to outline one possible scenario out of a number. The objectives for this kind of exploration are pretty self-evident. We want to visit the bodies surrounding other stellar systems. We want to seek signs of life or intelligence. And in the long term, perhaps human colonization of other stellar systems is going to be possible. Now, the fundamental problem with interstellar travel is a very obvious one. The distances are very large. You can read all these. They don't really give you a grip on what these distances really mean. However, my wife read the outline of this talk at one time, and she figured out that if you look at the back of your hand and look at one of the little hairs on the back of your hand, and that hair represents the distance from the Earth to the Sun, then the nearest star is about 25 to 50 feet away. So that gives you a little sense of what the scale is. And the travel times that are associated with these are, of course, the things that really inhibit a great number of possibilities for exploration. Next subject. Next view. Now, there are lots of reasons for thinking about interstellar exploration. A lot of them are really self-evident. You've heard some of these many times before. Let me just comment on 3 of these because they happen to have a particular interest for me at least. One of the objectives of this kind of exploration is to find evidence of other life. There's a vast difference between this kind of exploration and the kind that you do by radio signaling or radio receiving. In principle, if life existed at some time billions of years ago, you might still find evidence of it. Whereas clearly they wouldn't be transmitting radio signals today. The second thing is kind of an interesting one when you think about it a little bit, namely that none of you are strangers to the galaxy. Every atom in your body was created many billions of years ago, some of them in the original Big Bang, most of them in the interstellar stellar furnaces since that time. So you're really a composite of galactic material. And the notion of looking around to see where some of your atoms originated is kind of an interesting one, I think. Finally, the excitement of it. use this quotation because this is really how I started off on getting interested in this field. And I think many of you probably were in the same situation or are in the same situation. Now the problem with this field is that although each of these reasons is interesting and to one or another person, some of them are really quite persuasive, to try to make a compelling case out of all this is really rather difficult. So I satisfy myself with a belief that the composite of all of these reasons is certainly enough reason to begin thinking about this very seriously. Next view, Brad. Now the problems that are inherent in this I think, are fairly self-evident. First of all, I think you'll realize that if you want to make some of these trips in a realistic time, and a realistic time could be many hundreds of years in this category, that kind of flight is very energy intensive, and I'll give you a scale I'm going to use for that later. Now, what kind of a time is really realistic? Well, I happen to think that the time from 50 years to 500 years is something you can contemplate. Something very much longer than that, I think is very questionable. But there are things that people and groups have done in the 50 to 500 year period, which I think are in some sense yardsticks. Now, the kinds of payloads that we're talking about, the scientific payloads are very well understood. There's really no mystery about these. We can design those today, they've been designed in the past. One of the best system designs on this was the old Daedalus project from about 15 years ago, the British interplanetary project. The second question is, do we want cruise of some kind? My predilection is that we want cruise, because my feeling is that we're not here just to find out about things, we're here to do things, to act on things. And Thomas Huxley, I think, expressed this very well with that motivation of his. But there are a number of issues. Humans are going to have an enormous number of problems on these kinds of flights. So we're very confident robots is one possibility that's been extensively discussed. And in the long term, some kind of a partnership between robots and humans has also been discussed in some way. So the first concerns are propulsion, or getting there, and the second one is the crew, or doing things. Next view, Bill. There have been a great many studies of interstellar propulsion. Bob Ford put out a neat little paper some years back which discussed a dozen or so possibilities. Probably by now 24 such candidates have been discussed, and you can divide these in a number of ways. I've just divided these into these 4 categories for reasons that are not germane to this speech. But in any case, there have been propulsion schemes devised under each of these 4 categories. Now, I have used a selection screening process to try to focus on one. Obviously, you can accuse me of rigging my screening process to come up with the answer I want. And in a sense, I have to do a certain amount of that. But they are fairly realistic criteria. I'd like these to be conservative in current technology. I have current technology in quotation marks because there was a question about that. I'd like to be able to use something that's not really vital or necessary for other human endeavors. I want a large payload capability. And the reason for this is primarily that ultimately I may want to slow down and actually land on some of these stellar objects with either reverse rocket propulsion or magnetic sails or some combination of other schemes. That dictates a large payload. I want this to be compatible with human interest spans, which means that I have to have a certain exploration speed capability. And I want something that I can cost within a factor of 2 or 3, and the scheme I'm going to talk about is susceptible to that. And I also want something for which there is a realistic infrastructure in existence now. In other words, this is not something that is all hypothetical proposals. This is something which we actually could begin to build right now if we want to. And the one that falls out of this screen is simply a fairly old idea, which has been updated rather recently: nuclear explosive-driven propulsion. Now, I think most of you know what this is all about, but let me just run through the sketch on the next view graph. This is an old idea. It was invented by Stan Ulam at Los Alamos. It was a major U.S. program at one time, and a lot of very eminent and respectable people like Freeman Dyson were involved in this Orion program. This was done mainly in the 60s, and their projections at that time was that by this time, right now, we would be flying 5,000 ton interplanetary spaceships around. Well, something that they didn't contemplate interrupted that nice schedule. There has been a revival of interest in the last 2 years. First of all, because there are some new concepts that are around, and secondly, because there is a considerable drive now, which some of us are involved in, trying to declassify a lot of the aspects of this program. For reasons that are not entirely clear at this stage, a lot of this program is still classified. It's time to declassify it. And finally, the last point is something which is just a happenstance of the times. There is a worldwide move now to decrease nuclear armaments. And, a real question arises to what you do when you get rid of nuclear armaments. And one of the things you can do with them is reconfigure them and use them as propulsion systems. So you're satisfying a number of objectives at the same time. Now, the techniques are all, I think, fairly self-evident. When you explode a bomb, you turn it into a very fast expanding debris cloud. And that debris cloud is the propellant. It exerts a pressure impulse on a piece of the spacecraft that it hits. And when you work through the mathematics of this, and this has been done a number of times for both the old ideas and the new ideas, it turns out that you can get a total velocity of the spacecraft with many explosions, so that you keep the G loadings down for any single one, to be a substantial fraction of the velocity of this expanding debris cloud. And the number of 3,000 kilometers a second is one that I'm going to keep using. Now, there are a number of interesting characteristics for this kind of a system. First of all, this is a disposable propulsion system. It doesn't have any conventional material constraints on the engine. The purpose of nuclear weapons is to generate by high temperatures and destroy themselves in the process. Whether one appreciates it or not, people in a number of nations have been able to design very high reliability into these systems. And in contrast to many other systems, you can tolerate failures in this. If one of these, or two of these, or three of these bombs fail to go off, you don't lose anything except a very slight velocity gain. The system doesn't fail catastrophically. The total operating time is a few hours instead of, in some cases, years or decades. And these are all factors which, in a sense, are well adapted to some of the Model T versions of interstellar exploration, which is what I'm concentrating on. I'm not going to concentrate on the possibilities in the long run, but just what you could do right now if you said you might be doing it. The next view graph. The next view graph just shows you, for those of you who need reminding, what some of these configurations look like. The one on the left is the one that was worked on extensively 20 years ago, in which the bomb is exploded behind that pusher plate. By a complicated shock absorber and energy dissipation mechanism, you ameliorate that great shock loading to something which, in this particular case, was very tolerable to humans. They were talking about 1 or 2 G accelerations in these systems. One of the proposals that's come up recently, although it was discussed in a very brief form by Dyson during the early program, is the one in which you pull the spacecraft rather than push it. And without going into the details on this, one of the main advantages of this, as you can see from the diagrams, is that you capture a much larger solid angle of the expanding debris cloud with the system, so it's inherently more efficient. The next chart, please. what can you do with this kind of a propulsion system? And I'm not going to go into any of the equations which are necessary to derive the numbers that I show. But let me just give you what the outcome is. We've looked, and many other people have looked, at a fairly large range of vehicle velocities, from 1,000 kilometers to 30,000 kilometers per second. And kind of a horseback estimate of how feasible each of these velocity increments is based on what we know about nuclear weapon design and other things is also listed. That's the likelihood of getting these. And then just the transit time that these turn around into, we talk about a relatively near star, 4 light years, which is a little more than the one that's closest to us, but it's a great deal bigger than the distance between stars in the center of the galaxy. So that's kind of a rough estimate, and what you get out of this is if you can get 3,000 kilometers a second, you've got a 400-year transit time, which in my ground rules falls within the tolerable transit times, quality. We'd like to get higher velocities, 10,000 to 30,000 kilometers a second. Once again, the energy that is implied by this is something that's not easily grappled. If I tell you, and you can make this calculation yourself, with the Saturn V, which all of you saw many years ago, represented an energy expended in delivering that lunar payload vehicle of something like a few times 10 to the 13th joules. That's a number. It's a big number. But let's just use that Saturn V energy as the yardstick. Then it turns out that if you want to accelerate 1,000 tons of vehicle to 3,000 kilometers a second, and that's the basic case that I talk about, that's the equivalent of 400,000 Saturn V's. 400,000 Saturn V's turns out to be a tenth of the annual electrical energy produced worldwide. It also turns out, purely by a coincidence, to be about what is inherent in the energy of the nuclear weapons that people want to dispose of today, which is also about 4 million Saturn vehicles. So the bottom line on this is that with existing nuclear weapons, we have about 10 times as much energy available in the form of a very compact energy source as we need to get 1,000 tons of vehicle to 3,000 kilometers per second. But Bob mentioned that he and I have been interested in antimatter for a number of years, and both of us still are. There's a program going on now of a certain sort. It's clear that there's a lot of growth potential in all of these numbers, and it's clear when you run through the numbers that one of the ways to make this growth potential happen is to use large amounts of antimatter. Unfortunately, the large is in fact large. But there's no question that I can drive much more mass to much higher speeds, given that I have a large enough amount of antimatter. Now, the issue that I think is interesting here is that for the exploration strategy that I'm going to be talking about, there's really no great incentive to use very high velocities. I'll get back to that in a minute or two. Would you put on the next view, Greg? The other part of the problem that I mentioned is the issue of cruise. And I mentioned that for a lot of reasons there are real benefits to having cruise if you want to do things instead of just observing things. Now the problem you find here is that there are a great many practical issues on trying to make humans survive these very long interstellar flight durations. And although every item that's on this in this first bullet, life prolongation, cryobiology, suspended animation, genetic reconstruction, there's actually research work going on in all of these fields. The problem is that there's absolutely no measurement that you can make that says this is going to eventuate in anything at any time that we can foresee. So prudence simply suggests that if we're interested in cruise, that we need a replacement or a complement to human cruise. And the kind of crews that are inherent in this kind of a task, for reasons that I think we'll see a little later, are these so-called von Neumann robots, which were first talked about by Johnny Van. Actually, in 1948, there was a very prescient set of discussions that he had. he listed all of the things that had to be present in order for self-replication and universal constructability to be in place. And it just so turned out that 5 years later, this is exactly everything that he mentioned was found in the DNA codes. He had a lot of vision. Now, the theory of these von Neumann robots is quite well understood. There are 5 books that tell you about them. The problem is that the state of the technology today is not up to this, and the fundamental limits occur in the 3 items that I've listed. But people have speculated that things could come together in 50 to 100 years. Now, the reason that this is interesting is again, goes back to some of the things that John Lewis mentioned. He mentioned the availability of material from the asteroids. Galactic evolution theory, for whatever it's worth, does say one thing, that it says that within our galaxy, things ought to be pretty much the same everywhere. So the fact that there are materials for construction in our vicinity implies that there are very likely materials for construction in almost any vicinity in the galaxy. So that in fact you can use materials from anywhere in the galaxy. Now there is some work going on in this field also, although it's pretty abstract work at this stage. Why don't we go to the next one? Now what I want to talk about is not simply sending a ship out to look at something, but actually to generate a systematic exploration. And that's the reason why I like to use the analog of the Polynesian island migrations, which is probably the closest analog that you can visualize to this. I don't know how much you remember about the Polynesians, but they're a very, very interesting ethnic group. Starting from Indochina and South China, probably about 4000 BC, they spread very fast and very wide. Up until AD 1500, they were the ethnic group that had the greatest geographical distribution in the world. This was from a people who did not use metals, they had no formal script, and so on. And what they did, they finally settled on something like 300 of the main island groups. In the Pacific is one case. They stretched from Madagascar in the west to Easter Island in the east, and there's some evidence that they went into British Columbia and other places. The way they operated as an exploration strategy is that they would transport essentially their civilization on a bunch of these rather remarkable sailing ships. They would carry everything with them: people, livestock, food, plants, water. And they would set up a temporary civilization on the next big island that they found, and then they would rebuild or replicate that civilization over the next few generations. And when that civilization had reached a stable condition, then they set out for another exploration. So what the strategy amounts to is not simply exploring, but transferring civilization from site to site, and then using that civilization to build the tools so that you can carry on that exploration. That's how they did their exploration. And this is the analog that I want to use for systematic interstellar exploration. Starting off with precursor missions, in which we could begin now to test the basic things that we want to find out about. And then a first stellar contact is phase 2, and then a full exploration of a local stellar system to phase 3. And local means the closest 500 to 1,000 stellar systems. Now, one of the consequences of this brings me back to a point which I mentioned earlier, and that is that the time between stellar contacts now, exactly on this model of the Polynesian island migrations, the time is the sum of the travel time, which in the case of the Polynesians is negligible, plus the time to rebuild or replicate your industrial civilization, whatever level of industry you were used to. And just as a horseback guess for the sake of this discussion, let's say that the sum of that is 400 years plus 400 years. 400 years for the transit time and corresponds to the 1% of light velocity, transit speed. If you could go faster, you could cut that down. But the fact of the matter is you come out with a very interesting number. Even at this extremely conservative Model T exploration strategy, where it takes you 800 years to get from one star to the next, you would still have explored the entire Milky Way galaxy in something like 10 million years. And this raises an immediate problem, which is one of the reasons why there's a big schism between large groups of scientists. And let me go on to that in the next few minutes. There's one very prominent group which argues sort of as I've indicated here. Even with this Model T exploration system, and remember that this is predicated now on using things we already had, nuclear weapons propulsion device. We're talking about exploring the entire Milky Way galaxy in 10 million years. Now the problem arises when you look at the ages that are inherent in the systems around us. The galaxy that's perhaps 15 billion years old. It has maybe 200 billion, as many as 200 billion planetary systems in it. The Earth itself is old, but it certainly is much younger than the galaxy. And life above a certain complication level has existed on Earth for a billion years. And the point is that the galaxy exploration time, even with this Model T exploration strategy, is extremely short compared to these times. And therefore, the implication is, and this is the implication of this group that is on the con side of our group, since that exploration time is very short compared with any of the lifetimes of the objects that are in the galaxy, if life is not uncommon in the galaxy, that means that it exists in several places at least. It doesn't have to exist in very many places, but it exists in several. There's no reason for us to be the first explorers. Other intelligent beings could have risen before us, and the whole galaxy could have been explored, and maybe you should think of it as having been explored many times already. And that raises the problem that people like Enrico Fermi encapsulated very well. If this is so, if they existed, they would be here. The same group that has this rather pessimistic view of life in the galaxy then goes on. Let's put on the next view graph. This group, which includes people, or included people like Fermi and Neumann, and today includes people like Freeman Dyson and a number of other prominent astrophysicists and physicists. They will argue, as this view graph sort of indicates, we haven't seen any artifacts or monuments or messages from this intelligent life. And furthermore, you can make a number of arguments, and these are done very well in a number of places, that things are very, apparently a number of very improbable things occurred to make us happen in the first place. I think one of the best books to read about this is probably the Barrow and Tipler book, The Anthropic Principle in Cosmology. But there are lots of things which puzzle a great many people, and one of them is this coincidences in the values of natural constants. If you make a calculation, for example, that says that one natural constant is the fine structure constant, another one is the ratio of the electron mass to the proton mass. If they differed by more than 10% from their present values, you would not be able to chemically build long chain molecules. And particularly, you couldn't build the DNA molecule. And that's the kind of sensitivity which these people worry about. And that's the source of the quote from Freeman Dyson. Now this group agrees on one thing. They think that interstellar probe has actual physical contact would be the way in which advanced civilizations would explore the galaxy. In other words, they relegate radio signaling and radio communication to a very secondary place. But they say that the failure to observe either the probes or the remnants of probes or other artifacts implies that we are the only technological civilization that now or ever has existed in the galaxy. If you believe that, there's very little motivation for interstellar exploration. And that's where one side of this current scientific debate falls on. There is a group, a very large group of eminent scientists that do actually believe that we are the only technological civilization that's arisen so far. Let's move on to the next chart. There's the obverse of that coin obviously exists, and it has existed in many places also. And this group includes people like Carl Sagan and a number of other people who happen to have somewhat of a biased interest in space exploration, but nevertheless have thought about this fairly deeply. First of all, let's agree that it's improbable that intelligence can evolve, and in fact it did evolve at one time, assuming that we're the exemplar here. We're not in any very special region of the galaxy, and therefore all regions are as conducive to the evolution of intelligence as our region. And then they argue away this lack of evidence question by the arguments that are listed under the second bullet. You can think of circumstances in which a civilization which could do interstellar exploration would choose not to initiate it or to halt it at some stage. But there are even more basic questions, and that is, what are we looking for if we want to find evidence of past interstellar exploration? There are lots of reasons why this might be a very much more subtle issue than 2001 and 2010 sort of indicated. And some of the arguments are listed under that second one. And this has led to the counter by Martin Rees, who is an astrophysicist and cosmologist, which simply says that even if we don't have any evidence, that doesn't mean that we have evidence of the absence. And that's where the argument essentially boils down. There are two groups that have directly countering arguments on this. Clearly, my predilection is to believe the second group. I think we cannot rule out the fact that we are not alone in the galaxy, and we're not alone, and wouldn't be alone in the future. And therefore, there is, I think, ample motivation, at least as far as I'm concerned, for doing this kind of exploration. So let's talk a little bit about the details of the strategy that are involved, and go on to the next view. I want to talk about three phases for this, and the first phase I've written about elsewhere in great detail, so I don't want to repeat this, but in any case, the argument here is that there has to be something of a precursor nature where we begin to learn how to do some of these things. In other words, have practice missions and have test beds and so on. Even though these are precursor missions, if they're really to be preludes to true interstellar travel, they have to satisfy a number of criteria, and those are listed under the second bullet. And what comes out of this is that precursor missions to Tau and the inner Oort cloud are sort of the ones that make a lot of sense for a number of reasons. And if you go on to the next view graph, those are some of the reasons. Tau missions have been extensively studied for at least 20 years. There are fairly large JPL studies on that, for example, which are updated in a number of places. We know pretty well what we want to do and what to do it with. Instruments have been defined in pretty great detail. Going out another factor of at least 10 in distance to the inner Oort cloud has a number of interesting implications. First of all, this tells you a lot about whether we really understand interstellar dynamics or whether we don't. Secondly, there have been a number of proposals that use comets as transport means or for raw materials or for human settlement. If you remember John Lewis's comment that a lot of the asteroids have arrived from cometary parent bodies, you'll see why this is an interesting case. Now, the Model T version of this precursor mission that I'm interested in, and again, this is discussed elsewhere, I feel is fairly inexpensive as space missions in general go, and certainly as interstellar missions go. And I think this is something that we could begin serious pragmatic work on now if we had the will to do so. And we would accomplish these missions within a lifetime, certainly many of the younger people in the audience. If you go on to the next view graph, we go into the phase 2 missions. This is the mission at a time where we actually extend the flight to a true interstellar flight, make at least one stellar contact, and a number of improvements in the technology simultaneously put in train. And this is a way of running an all-up test to see whether we're really ready for the interstellar flight this way. Now, both in the precursor mission and in this mission, but particularly in this mission, you have an enormous psychological impediment. And it's a psychological impediment which is something that you can sense. And the issue is, why should we start with a Model T version of an interstellar program? If we only waited 50 or 100 years or 200 years or 500 years, we'd be bound to have better technology. And then we could do these things much better. And the vision that people always have is that you launch a Model T mission someplace now, and when it arrives, missions that came after that have already happened and got there much faster. And this antiquated object is greeted with hoots and derision as it comes in. I happen to believe that that's probably not the realistic thing. I think people would be very impressed, you know, if somebody in the Renaissance time launched a rocket to the moon, and it just was arriving today. I don't think we'd deride that too much. But the point is that here is the point where the sticky issue really arises, because there is simply this enormous temptation to not do anything, because the argument is that if you just wait for a while, things are going to improve so that you do things much better. And the arguments against that fall into the category, if you don't do anything, you're not going to get the motivation to make these better things happen anyway. So it's hard to see how you can avoid the requirement for doing something, even though it's a Model T version to begin with. And now for the next view graph, the phase 3 missions. This is a phase in which, if you use the systematic exploration program, you explore essentially the whole Milky Way. And you do exactly as the Polynesian island migrations occurred. You hop from stellar system to stellar system. And you use the crew on each stellar system to replicate the industrial level required to give you the rocket and the crew to go on to the next system. And as I mentioned earlier, in this strategy, there really isn't an enormous incentive to reduce the transit time to get very near light velocities. The time to rebuild and replicate the civilization is bound to be an important component of this. The other point is this is still a very low-cost system, because parent Earth only pays for the first complement. The first few ships that leave this go on to the first interstellar missions. After that, they're all on their own, essentially. And the problem that you have there is that it is perfectly possible that the Earth as a parent place for civilization might well disappear in this interstellar exploration. And that's an occasion where I think it might occur to a very advanced civilization to simply stop exploring. The whole point of exploring is to show parent civilization that there is or was not life elsewhere. And if that parent civilization disappears, that motivation also disappears. But the other side of this is that this is a kind of a strategy which we've already had experience with, at least the Polynesians have had experience with. Going on to the next view graph. Can we begin an interstellar exploration program now? Yes, we can. At least for the precursor missions, which correspond to the inshore expeditions of the Polynesians. We have enough energy in compact form in nuclear weapons available to do this and do it pretty large and complex and very flexible payload. The technology that's involved in this is quite well understood for a number of reasons. So there are some circumstances favoring this beginning, and that is some of the things I've just mentioned. The technology base is really here. Remember, we're not talking about sending von Neumann robots with these precursor missions. We have the basic ideas in hand on nuclear explosive propulsion. We also have an opportune time in many ways. This is a time when a lot of people want to have international cooperation of a magnitude hitherto unfelt, and one of the evidences of this is the enormous impetus to reduce nuclear armaments. This would be an opportune time to say, let's reduce them, but let's use them for this kind of operation, which, if you think about it, has a number of advantages compared with other uses for these. Proposed of taking the nuclear materials out of nuclear weapons and storing it someplace is just really an enormous temptation. Trying to convert it into civilian reactors causes all kinds of technical and political problems. So there is an opportune time right now because we do want to get rid of nuclear weapons as armaments and use them for this particular purpose. Will we begin? I think that's extremely unlikely. I think that we don't have the will, we don't have the commitment. We're going to sit around talking about this for a very long time. The irony is that we could begin because we do have the technology and infrastructure to begin. Okay, the next to last chart. There are a number of things that are both going in our favor and not going in our favor right now. The notion of using adaptations of nuclear weapons as propulsive engines is still going to be foreign to a lot of people. But from my examination of what has gone on in both incidental tests and a lot of analysis, this is not something which is visionary. It really is current today. And I personally find it very hard to think of a more compelling kind of question or set of questions to think about. This question of whether there is or was life elsewhere, or intelligence elsewhere in the galaxy, I think is a very compelling one, at least to me. Even if we find out that we're not alone, we're just part of a large community which has been not in contact heretofore. Maybe we're still unique or special in some way, but you have to encounter this in order to find out. The thing that is surprising is the speed with which this kind of a systematic exploration can proceed once it's initiated. A 10 million year period to explore the whole galaxy is a tiny slice of the time that the galaxy has existed, the time that life has existed, even on Earth, let alone possibly elsewhere. And the way this, I think, becomes particularly interesting to you, if you think about it, is that if you take two time periods, one of them, the time period from the appearance of the first hydrogen, which was a pre-man precursor who walked on 2 feet instead of on 4 feet, and who had certain brain adaptations in order to make this happen. If you take the time period from the emergence of that particular species of being on Earth to the time from now until we could have explored or could explore the whole galaxy with a systematic exploration capability, they're just about the same, which tells you how fast things can move. And I particularly recommend that last quotation from T.S. Eliot to you because I think this is one of the things that captures really the spirit and purpose of a lot of the motivations that you could adduce for interstellar exploration. So let me quickly summarize on the last chart, last few minutes. sort of my conclusions are. First of all, these are clearly extremely tough problems. Even the precursor missions will be very tough problems. But the way things have happened in the last 20 years, I think those problems have turned insurmountable to merely challenging and only merely invitation. Second, we already possess the kind of technology with which we could do this if we're content to say we're going to use Model T technology. The third point is that there are a number of motivations for doing interstellar contact attempts. I think each of you may have a personal motivation of your own. Fourth point is that we can model a systematic exploration strategy. By systematic, I mean essentially exploring the whole Milky Way, not just a random hop to some star for some purpose. We have a model in past human endeavors. That exploration period is bound to be long, millions of years, probably. But the role of the Earth directly is a very brief part of that. There are central human issues which only interstellar exploration can confront, and one of them is the one which I mentioned earlier. If you believe or side with one of the schools of scientists, there is every reason to believe that there may very well have been past civilizations that tried interstellar exploration who no longer exist. Now, the only way you're ever going to find that out is by physical contacts. Radio signaling is no contact. The next bullet is that there is an opportune time now, in a sense, because there is a great political and social impetus to reduce nuclear armaments, and this would be a wonderful way to transform those nuclear armaments. And the last point is something which I think I feel very strongly about, and that is that this is not an issue, if we talk about precursor issues, at least, this is not an issue which need be hypothetical. We have the technology infrastructure, the basic knowledge infrastructure to begin that if we want to